everyone, welcome to the classes on fluid machinery. Today is our last topic on fluid machinery, that is axial flow reaction turbine. So in axial flow reaction turbine, we will be discussing in detail about Kaplan turbine. We have two types of axial flow reaction turbine, propeller turbine and a Kaplan turbine. Here is a schematic view of a Kaplan turbine. The water will be entering from this side and it will be flowing in an axial direction. This is the axis of the turbine. The water flow is along the axis, parallel to the axis. That is why it is called axial flow reaction turbine. And this is the blade. The blade is attached to the center portion of the runner, that is called boss or hub. Center portion of the runner is called boss or hub, and the vanes are attached to the circumference, along the circumference of the boss or hub. So water will be flowing through the outer surface of the boss and through the between the vane blades. Okay, so the flow of water will be in the shape of a hollow cylinder. Okay, the flow of water will be in the shape of a hollow cylinder, and the outer diameter of the hollow cylinder will be outer diameter of the vane DO, and inner diameter of the hollow cylinder will be inner diameter of the vane DB. Okay. And at the end of the turbine you can see a draft tube. The purpose of the draft tube is to increase the pressure of the water coming out from the turbine. As it is reaction turbine, there is a chance of reducing the pressure inside the turbine to a value less than the atmospheric pressure. If the pressure is less than atmospheric, the water will not come out from the turbine. So to make the flow easier, we will be increasing the pressure of water coming out of the turbine by a tube, which is that is called a draft tube. The area of cross section will be increasing as the flow progresses. Okay, and while doing the problems in draft tube, we will have new equation in for the discharge. I have already mentioned the discharge will be in the shape of a hollow cylinder. So area of flow will be, equation will become pi by 4 into equation of a hollow cylinder, that is pi by 4 into d outer square minus d inner square. So d inner square is the boss diameter, d outer square is a do square. Here it is written do cube, please correct it as do square. Okay, and we will be analyzing the starting and ending point of the flow direction. Here it is marked point 1 and point 2. Both these points are at the same distance from the center of the runner. Normally we will be marking the blade velocities as pi d n by 60, where d is the distance from the center of the runner. Okay, for point 1 and point 2 are at the same distance from the runner. The blade velocity for the Kaplan turbine will be same, so it will be u1 and u2. So in most of the problem we will be analyzing the outer edge. In some problem they will mention that we have to calculate the blade velocity, or we have to calculate the blade angle at the middle of the runner. So in that case we will be using the equation do plus db by 2 mean to get the mean diameter of the runner. Okay, so as per the question we have to calculate the diameter and speed of the blade. So if it is mentioned at the outer edge, you can use the outer diameter. If it is at the mean or at the middle of the blade, we have to calculate the mean diameter and use that. Okay, so this is the equation for discharge, this is the equation for blade velocity, which is same, and velocity of flow will be same, vf1 is equal to vf2. Here is our first question. A Kaplan turbine working under head capital H is 20 meter, develops 11,772 kilowatt shaft power. Shaft power is given as, the outer diameter of the runner is 3.5 meter, DO is 3.5 meter, hub diameter DB is 1.75 meter. The blade angle at the extreme edge of the runner. Here it is not mentioned whether it is alpha or beta. Okay, we will go forward. The hydraulic efficiencies of the runner of the turbine are 88% and 84%. The velocity of whirl is 0 at the outlet. Velocity of whirl at 0 is at the outlet means beta is equal to 90 degree. So we can understand this 35 degree belongs to alpha. Okay, the things we have to calculate is the runner vane angle, that is alpha at the inlet and not alpha, theta at the inlet and phi at the outlet, and the last one speed of the turbine. So here is our velocity triangle. Velocity triangle is almost similar to reaction turbine, that is a Francis turbine or radial flow reaction turbine. We have to calculate the value of theta. First one, theta. Tan theta can be written as opposite side by adjacent side. So tan theta is equal to opposite side vf1 divided by v omega 1 minus u1. So we need the value of Vf1 and V omega 1 u1 for calculating the value of theta. So we need the value of Vf1. So Vf1 can be found out from the equation of Q. Q can be written as area of flow into Vf1. So if we know the equation for Q, we can calculate the value of Vf1. For getting the discharge, we need compare the shaft power and the water power for a overall efficiency. Overall efficiency is equal to shaft power by water power. Shaft power is given. The equation for water power is rho gqh, and h is given. We can calculate the value of Q. Okay. So we'll use the equation of overall efficiency shaft power by water power. From there we can calculate the value of Q. Okay. Q can be written as 7.4280 meter cube per second. And from the Q we can calculate the value of Vf1. And from the triangle, if we know the value of Vf1 and if we know the value of alpha is given as 35 degree, we can calculate the value of Vw1. Okay, by using the equation we can calculate the value of Vw1. Tan alpha is equal to Vf1 by Vw1, or we can calculate the Vw1 as 14.14 meter per second. So we got the value of Vf1 and Vw1. Next we need the value u1. For that we will be using the efficiency, hydraulic efficiency, which is runner power by water power. So runner power is given by V omega 1 u1 plus or minus V omega 2 u2 into rho a v1 or rho q divided by water power rho gqh. So rho and q get cancelled. The remaining term will be V omega 1 u1 divided by gh. So substitute the value. We will get the value of u as 12.21. So we got all our values. So we will be calculating the value of tan theta is equal to Vf1 by Vw1 minus u1. You will get the value of theta as 78.58 degree. Next we will calculate the phi. Tan phi is equal to Vf2 divided by u2. Since Vf1 and Vf2 are same and u1 and u2 are same, we will be using the same formula and we will calculate the value of phi. And the next thing we have to calculate the speed of the turbine. u1 and u2 is equal to pi do, outer diameter, into n by 60. We can calculate the value of rpm as 66.63 degree. So we have calculated all the required value, that is RPM and RPM as 66.63 RPM, and the tan, theta and phi are the things we have to calculate. So we'll go through our next problem. KAPLAN turbine develops 24.647 kilowatt power. So it will be shaft power at an average head of capital H is 39 meter. Assume the speed ratio. Speed ratio you will be calculating for calculating the value of U. Speed ratio to flow ratio 0.6. Okay. Diameter of the bow is equal to diameter 3.5 times diameter of the runner. Okay, the outer, sorry, dB is equal to 0.35 into do. The overall efficiency is 90%. Calculate the diameter, speed, specific speed of the runner. Okay, first we need the diameter of the runner. Diameter we can use the equation of Q and Vf1. Okay. So Vf1 can be calculated using the flow ratio equation. Flow ratio is given as 0.6, and from the equation of flow ratio we can calculate the value of Vf1. Okay. Next thing we will be calculating the diameter from the equation of Q. The Q can be calculated by comparing the shaft power and water power. So we will get the value of Q. So in that Q, we will substitute Q is equal to pi by 4 into d outer square minus d inner square, and we will get the value of diameter. That is the first thing we have to calculate, the diameter of the turbine. Okay, second thing we have to calculate the speed. Speed is given by u is equal to pi dn by 60. So since the u is not given, we can use the equation speed ratio equations. In the speed ratio is given as 2. So speed ratio divided by root 2g is equal to u, or u root 2g is equal to, we'll get the value of u as 55.32 meter per second, and u can be compared with the pi dn by 60, and since the diameter is known, we can calculate the value of rpm. Okay, so we have calculated the diameter and the specific speed is calculated. Last speed is calculated. The last thing we have to calculate the specific speed. Specific speed of the turbine is given by n root p by x raised to 3 by 4. All the values are known. Calculate the value of specific speed. Okay. Here is our last problem for the KAPLAN turbine. In a tidal power plant, a bulb turbine, which is basically axial flow turbine, operates a 5 megawatt generator. So the output of the generator is 5 megawatt at 150 rpm under a head of 5.5 meter. The generator efficiency is 93%. Okay. And the overall efficiency of the runner is turbine is 88%. So generator efficiency means by using a turbine we will be supplying power to the generator, and the generator is developing power depending on its efficiency. Whatever power is transmitted to the generator, it may not be converted into total power. It will depend on the efficiency of the generator. So that is the term generator efficiency. Generator efficiency will be output of the generator divided by input of the output of the turbine. That is the generator efficiency. Next thing, the diameter of the runner is 4.5 meter, hub diameter is 2 meter. So DO and DB is given. Hydraulic efficiency is 94%, that's given. No exit wall, that means VW2 is equal to 0 and beta is equal to 90 degree. Determine the runner vane angle at the inlet and exit at the mean diameter of the vane. Okay, normally we will be using the equation at the end of the vane. Here it is meant at the mean diameter of the vane. So for the equation of U, we will be calculating the mean diameter. Normally we will be calculating U based on the outer diameter, so we will be calculating the mean diameter. So the only difference is for calculating the blade velocity U. So here we will be using the mean diameter, outer diameter plus inner diameter by 2 for calculating the blade velocity. And the other difference is the generator power output is given as 5 megawatt. It is not equal to the shaft power. Shaft power is converted into generator power by using some equation for efficiency. So that is called the generator efficiency. So here is the given data and first we will calculate the runner vane angles. So vane angle again will be tan theta and tan phi. Tan theta is equal to Vf1 divided by Vw1 minus U1. So we need the value of Vf1, Vw1 and U1. So Vf1 can be calculated from the equation of discharge. For that we have to calculate the discharge. Discharge can be calculated from the equation of overall efficiency and shaft power. Shaft power is not given, here it is given the power output of the generator. So from the power output of the generator we will calculate the value of shaft power first. So shaft power is the output of the turbine, which is the input of the generator. Okay, the turbine output is connected to the generator input, so output of the turbine will be the denominator and the output of the generator will be at the numerator. That will give the generator efficiency. From that we can calculate the input of generator or the output of the turbine, that is called the shaft power. Okay, if we got the value of shaft power, we can calculate the value of water power by using the equation overall efficiency equal to shaft power by water power. Water power is equal to rho GQH. From that we can calculate the value of Q. Okay, if we got the value of Q, next we will be calculating the value of mean diameter and mean speed U1. Okay, so mean diameter can be calculated by using the diameter of the outer diameter and hub diameter. We will calculate the mean diameter, and based on the mean diameter we will be calculating the equation U1 and U2. Okay, next we will be calculating the value of Vw1 by using the equation hydraulic efficiency is equal to Vw1 U1 by GHA. We get the value of Vw1. So we got a Vw1 U1, and one more thing we need a Vf1. So Vf1 can be calculated by using the equation Q is equal to pi by 4 d square outer square minus inner square into Vf1. So we get the value of Vf1. So normally we will be using the velocity triangle like this, but here we got the Vw1 as a 1.987 and U1 as a 25.52. So in our triangle, in general triangle, U1 is the smaller value, Vw1 is the larger value. So this velocity diagram will not suit for our question. So our question will be changed to new model. Here is our velocity triangle. In this U1 will be the larger value and Vw1 will be the smaller value. Vf1 will be the vertical component. So Vr1 will be shifted to the right side of the triangle. Okay, so we will be writing tan theta is equal to again Vf1 divided by U1 minus Vw1. Okay, so the condition is if the value of Vw1 is less than U1, we have to redraw the triangle as like this. So Vf1 is the vertical component, left side it will be V1 and right side it will be Vr1. Okay, so tan theta is equal to Vf1 divided by U1 minus Vw1. So we will get the value of tan theta and we will calculate the value of theta. So next thing we will be calculating the phi. Tan phi is equal to Vf2 divided by u2 will get the value of pi also. Okay, thank you.